So far we've been solving exponential equations. We're going to turn now to log equations. And this is where we're really going to start to see the payoff of all of those rules of logs that we learned in the previous section. So we've been using the power rule of logs, that if I have the log of something to a power, I can bring that power down. We've been using that one a lot. We haven't really used the product and quotient rule of logs yet. We're going to use that with log equations because my goal is always going to be to get the equation into one of these two forms. Essentially, just like with an exponential expression where we wanted to isolate the an exponential equation, where we wanted to isolate the exponential expression, we need to isolate the log expression. So you either need to have a log by itself equals a number, so that way the log is isolated on one side of the equation, or you need to have the log base b of this equals the log base b of that. There you would have two logs, okay, but they're each isolated. The only thing on the left side is the log base b of this. The only thing on the right side is the log base b of that. Okay. Once you can get to that form, if you have one log equals a number, we're going to just do our familiar rewriting this in exponential form. So my base would be b, my result would be this, and the exponent is that number. But notice, that's going to give me b to a number. That's just going to give me a number. That's going to give me an equation that now no longer has any logs in it. Okay. And if I have something like this, I can use the fact that logs are also one-to-one functions. So if the log base b of this is the log base b of that, that's going to imply that this is equal to that. Okay? I can go straight there by saying logs are one-to-one, or that's equivalent to just taking b and raising it to both sides. That would undo the log in both cases. Now, in both scenarios here, we go from an equation that has a log in it to an equation that doesn't have a log in it. Anytime you have a log, there are restrictions on your argument. And generally speaking, our argument is going to be where our variables are. We're going to have variables in the thises and the that's, as I've written it here. Okay? So there are going to be some restrictions on things. So this can only be true if this is positive. This thing has to be positive. Otherwise, I'm going to get something that just isn't true. Okay. And here, both arguments, what I'm calling this and what I'm calling that, both have to be bigger than 0. Now, it's possible that when we try to solve our equations, and we go from the versions with logs to the versions without logs, it's possible we're going to have some numbers that are solutions to these equations that are not solutions to these original equations. So with log equations, it is always going to be necessary to check that your solutions ensure that all of your arguments in the original equation are positive. You don't actually have to plug back in and make sure that it works. You don't need to do a full check that way, but you need to check that you haven't violated any restrictions. So let's look at an example, and I've actually just selected some even numbered examples from the text to take a look at. So this is problem number 50. It says the log base 3 of y plus the log base 3 of y plus 6 is going to equal 3. Now, I'm going to try to remember the first thing I'm going to do when I have a log equation is I'm going to look at what my arguments are, what those things are that I'm plugging into the log, and I'm going to immediately record those restrictions. Y has to be bigger than 0, and y plus 6 has to be bigger than 0, which means y is going to be bigger than negative 6. Now, of course, if y is bigger than 0, it's also bigger than negative 6. So I really just need to check that one restriction. Okay. The reason I'm doing that is because it's so easy to forget. Here, I can see that y has to be positive and that y plus 6 has to be positive. But I'm going to solve this by getting rid of those logs. And once I get rid of those logs, I'm not going to be able to see that. So I like to write those restrictions first. That way, if I forget, I have the whole rest of the time that I'm working out the problem to remember and say, oh yeah, I'm supposed to do that. And as long as I do that by the end and check that my answers actually work, I'll be okay. All right, so now there are two possible forms I want. One log equals a number, or the log base b of this equals the log base b of that, where my base here would be 3, I can see. Okay. That's just a number. So I think it's going to be easiest to just get 1 log equals the number 3. But on the left-hand side, I don't have 1 log. I have 2 logs added together. Well, when I'm adding logs, I'm adding exponents. That corresponds to multiplication. So I can consolidate this and write that as the 1 log base 3 of y times y plus 6 is 3. And then I can do that multiplication. So that's the log base 3 of y squared plus 6y is equal to 3. Now I can rewrite that in exponential form. So the exponent I need when 3 is my base to get y squared plus 6y, that exponent, that log, is 3. But notice, 3 cubed, that's just a number. That's 27. So I've got 27 equals y squared plus 6y. So now I just have a quadratic equation in y. Now notice from here, it's not obvious that there are restrictions on y. It looks like it would be perfectly fine if y was a negative number, but I know it can't be. Anything that's a solution to this will also be a solution to this. But it's possible that my quadratic equation here will have what we call extraneous solutions. That's numbers that make it true, but don't make the original equation true precisely because they violate those restrictions. All right, so I would solve this by moving everything over to one side and getting it set equal to 0. So 0 is y squared plus 6y minus 27. I can factor or use the quadratic formula. I'm going to try factoring. Looks like that's going to be a y plus 9 times a y minus 3. That'll give me minus 3y plus 9y is my 6y, and there's my minus 27. Okay. So that means either y plus 9 equals 0 or y minus 3 equals 0. That would give me y equals negative 9. That would give me y equals 3. So I have 2 potential answers. Do I get to keep them both? No. I have to reject the negative one because any solution has to be positive and bigger than negative 6. Negative 9 is neither. It's not positive and it's even smaller than negative 6. 3, however, works, so that's my answer. So in this case, we did have an extraneous solution. So it looked like negative 9 was an answer because it was an answer to this second part, but it wasn't an answer to the original equation. Okay. Now, there will be some times when you solve a log equation and everything that you get as a potential solution actually works so that you don't have to reject any answers. However, in order to get full credit, you have to show me that you checked. That is a necessary step. Okay. So, even if we hadn't had to reject this, you would only get full credit if you had recorded these restrictions. Writing down these inequalities is enough to tell me that you checked. Now, if you write these down and then ignore them at the end, you're not going to get credit for checking your restrictions because obviously you forgot the second part, which was to actually check. But if you have a situation where everything that you got as a potential solution works, and you wrote down the things you needed to check, I will give you credit for checking. If you don't write them down, even if you have the correct answer, you did not show enough work to justify it. This is always a necessary step with log equations.